So now we're going to talk about reaction stoichiometry, which is sort of already obvious, I think. We've been practicing stoichiometry. Let's talk about what it means, okay? A balanced chemical equation provides a great deal of information in a very succinct format. So we need these because we can say a lot with just a few pencil strokes. Chemical formulas provide the identities of the reactants and the products involved in the chemical change. Coefficients provide the relative numbers of these chemical species, and the quantitative relationships between these are entitled sort of collectively stoichiometry. All right, so that's what stoichiometry is how much of one thing per how much of another. Okay, so here's what we're going to do. The general approach to using stoichiometric relationships is similar to something you might see in, say, making food. Okay, so oftentimes people, when they talk about stoichiometry, they might think of things like peanut butter and jelly sandwich, or bologna sandwiches, piece of cheese, 2 pieces of cheese per sandwich, whatever, 2 pieces of bread per sandwich, and so on. But another example that's often used is a recipe for making pancakes. Okay, so let's look at this. A recipe for making 8 pancakes calls for 1 cup of pancake mix, 3/4 cup of milk, 1 egg, and that makes 8 pancakes, right? So can you see the stoichiometric coefficients are 1, 3/4, 1, and 4, right? So before we move on, let me ask you, remember the definition we were talking about in a previous conversation about balance? What is meant by the word balanced? And we said whole number coefficients. So there is a number that's not a whole number coefficient. So if I wanted to make these all whole number coefficients, what would I multiply everything by? What would I multiply everything by? 4, right? 4, 4, 4, and 4. This would give me 4 cups of milk, of mix, 3 cups of milk, right? Because 4 times 3/4 is 3. 4 eggs and 32 pancakes, right? So that's what we would do if we were going to try to make this quote-unquote balanced, right? All right. So balanced chemical equations are used in the same way. From a balanced chemical equation, we can determine, number 1, the amount of one reaction required to react with another, and number 2, the amount of reactant needed to yield a given amount of product. The coefficients in the balanced equation are used to derive stoichiometric factors that permit computation, and by the factors, we're going to say ratios. That's what we're looking for. So let's practice this a little bit. If we have, let me go to a different color. If we're going to make ammonia, suppose we're going to make ammonia and we're going to make it from nitrogen gas and hydrogen gas. So this equation shows that ammonia molecules are produced from hydrogen in a ratio of 2 to 3, right? There's my 2 and there's my 3. So if I'm going to try to figure out, let's see, well, we'll figure some stuff out in a future slide. First of all, let's appreciate this, that there's 2 ammonia molecules for every 3 hydrogen molecules. There's 2 dozen for every 3 dozen. And there's 2 moles for every 3 moles, right? So it doesn't exactly matter how much we're talking about. It's the ratio that we're interested in. Okay, let me skip that slide and go down here. What mass of sodium hydroxide would be required to yield 16 grams of the antacid milk of magnesia by the following reaction? Okay, so this is going to take some trouble. We're going to have to, let me get a black marker here. I'm not going to solve it. I'm just going to show you what we would do to solve it, right? We have, let's see, what mass of sodium hydroxide, that's what I'm asking for right here. If this is mass, right, in grams, okay, mass, would be required to produce 16 grams of the antacid milk of a magnesia, 16 grams by the following reaction, okay? So what I would need to do is I would need to convert these using molecular weight or formula weight. I would need to convert this to the moles, because this is the only relationship I know. I know that there are 2 moles of sodium hydroxide for every 1 mole of milk of magnesia, right? Can you see that? That's the ratio that I know. And then once I get the moles here, I can use the formula weight to go to grams. So that's how we're going to set these up. I set this up sort of like a table. Can you see a table here? Let me go with light green. Can you see a table where this is like one row, here's another row, right? Here's a column, here's a column, here's a column, right? See what I did? And so I'm starting out with, the question is, how much of this do I start out with if I want 16 grams of that? So we're going to do this a lot. That's sort of a general layout. Let's look at, let's move on. I think we're not going to do, I'm not going to do out any examples here. I'm just going to show the layout, and then we'll do examples in different videos. Examples 4.8 in your book and 4.10 illustrate how we're going to do these stoichiometric calculations and why we need them. Numerous variations at the beginning and ending computational steps are possible depending on what particular quantities we want, right? And all of these calculations share a common essential component, that is the use of stoichiometric factors derived from balanced chemical equations. So let me go back here. This was the stoichiometric factor I had. A little difficult to see. I'm going to write it again in green, or rather in orange. There's 2 moles of sodium hydroxide for every 1 mole of magnesium hydroxide, and I get those numbers from here, right? There's a 1 there and a 2 here, right? Okay, stoichiometric factors. We definitely need them. We're going to use them a lot. And this is just an overview video, right? We'll do examples in another video.